So now the question that we have is, what is exactly a language model, right? So the best way to define a language model is a language model is something which can be categorized as a subfield of deep learning, natural language processing to be specific. It accepts an input as a prompt or a question, and the output that we are expecting out of this model is a text-based response. And what happens in the middle from the input to output is like the processing, where it analyzes the input and generates a response based on like all the learned patterns that it has learned during the training process. So now let's discuss our understanding of the language models using this small example. Let's see that we have a question, like one of the use cases is to predict the next word in the sequence. So this is a fill in the blanks kind of question. But the question we have been asked is, this is a sentence, and we have to fill in the next word in the sentence. So the sentence goes like this. Last night, I was reading Harry Potter and then you have to predict the next word in the sequence, right? So let's assume that we don't have any model as such. This is human beings which that we are asking this question to. If I were to ask you this question, that last night I was reading Harry Potter and then like, can you tell me what will be the next word in this sequence? We don't have to be correct, like just we can have any random guesses that we can possibly think of. So let's go back to the typical thought processes, how a human being thinks, right? So we think based on the context. So here the word says that reading. Probably we are talking about a book, right? And then we are talking about Harry Potter. So in what context have you heard this word Harry Potter? Anybody? Movie? Yes. So movie that was based on a novel, right? So we know that Harry Potter is a fictional character, which is a hero of a book. And there has been a series of book written on Harry Potter and something, right? So probably here what we are talking about is Harry Potter and if we look at the names of the books, probably that's what we are talking about, Harry Potter and the X or Y or Z. So the one that the word that we're going to fit in here is one of those words that appears in the names of or the titles of the novels. Yes, yes. So the language model also thinks similar to how we think. So these are the names of the books. So Harry Potter and the Sorcerer's Stone, Harry Potter and the Chamber of Secrets, Harry Potter and the Goblet of Fire, and so on. So probably we are talking about one of these words that which appear next to Harry Potter in the names of the novels, right? This is how we typically think about different things. Or if a human being is asked this question, that's how we are going to find an answer to this. So this is exactly how language model also works. So what it is going to do is it's going to scan through its learned database that like after Harry Potter, what is the frequency of occurrence of this specific word? And what is the frequency of occurrence of this? What is the frequency of occurrence of this and this? And then it's going to calculate all the probability of occurrence. And the one with the highest probability is the one which is it's going to fit in here. So the answer to this question will be philosophers, because when we are ranking based on the probability of occurrence, then this one wins. So now if I add a little bit of context to this question, and the context is here. Remember, I lived in New York and bought my book from the United States. So this is additional piece of information or context that I am giving to this language model. Now, how is this additional context important to us? Right? Like when I get additional information, I try to think, okay, how is this important piece of information changes my learning or changes my decision-making algorithm? So the impact that this statement has is the word sources is not that common in United States. So the US audience will not relate to the word sources properly. So that is the reason. Sorry, they will not relate to the word philosophers that properly. So the philosopher's word was renamed to Sorcerer's Stone in United States. So in the whole world, the book was released in the name of Harry Potter and the Philosopher's Stone, but specifically in the United States, they renamed the book to Harry Potter and the Sorcerer's Stone. So this is what the additional piece of information is going to, this is how it's going to affect my final outcome. So with this, obviously the Philosopher's Stone will not be that commonly available in the United States. And because the fact that I'm in the New York, probably I might have bought my book in the United States, which means that it's less likely that my book would be named Philosopher's Stone, and it's more likely that my book will be named as Sorcerer's Stone. Right? So language models, as we know, is more about context. So we have to store longer context in order to have more accurate prediction. Yeah, so this is what we are going to return, the sources. So next is, okay, we have a fair understanding of what a language model is. Now, what is large about it? We call LLMs, right? Large language models. So what is large about a language model here? So the large is basically refers to the massive scale that it is trained on huge databases, which has billions and billions of words. The model size, that is the deep learning architecture, actually utilizes in some neural networks or some transformer networks, which are huge in size. And apart from that, it also uses complicated algorithms and the way we are going to compute the probability computation. So this is possible if we have an infrastructure or a hardware that is capable of computing all these results in fraction of time, right? And and the last one is it uses unsupervised learning. That is, it should be able to learn from the raw text data without the need for explicit labeling. That we do not need a human in the loop to make sense or derive insights from our data. And what are the common examples of different large language models? The commonly used ones are GPT-3, that stands for Generative Pre-trained Transformer 3, developed by OpenAI. Then Lambda, which stands for Language Model for Dialogue Applications, developed by Google. And then BERT, which stands for Bidirectional Encoder Representations for Transformers, again developed by Google. And then this screenshot has a different, so all the major companies that are in the AI race are also in the large language model race. When I say LLM race, it refers to how quickly I'm able to predict data or how quickly I'm able to predict the next word in my sequence, and what is my response, like how minimum is my response time, and like how many different diverse patterns I can cover at a given point of time. So what are the major driving forces of computing? First is, of course, the faster computing. So when I'm asking ChatGPT a question, hey ChatGPT, can you summarize this document for me in 200 words? I don't want the response to be out after 1 hour. I want the response to be as quick as possible. So that is our faster computing. It should also use better algorithms so that my precision and accuracy should be good, and it should be able to churn more data. And what I expect at the end of the day is good value for money. And what lies in the middle is the magic box or my hardware AI infrastructure. So to summarize the challenges and limitations of the LLMs from the lens of a computer architect, first is the memory constraints and management. So we know that, okay, for training, we need a lot of data. Where are we going to store that data? We are going to store that data in a memory. So my memory systems has to be more efficient. I should be able to fetch the data and store the data in a very efficient manner, right? So that there comes the memory constraints and management. Next is the computational complexity and resource requirements. So I got to know about the memory, but my compute resources or my CPU or accelerator cores have also to be efficient enough so that they can accept the data and process the data in the minimum execution time or minimum response time. And then my latency and throughput considerations also I need to be very, very careful about. Now, what is latency? What is throughput? I understand response time, that when I have input then I will have output. So output time minus input time is my latency, right? So that's what we all have studied. So now what is throughput? So throughput seems little unfamiliar to me. So what is that in throughput, or where have you come across the word throughput in your teaching or research, or there? Any cues, any thoughts? Or why is throughput important? Why should I know about it?
Computations.
Yeah, so throughput is defined as how many data items I'm processing at a given point of time. So to explain it better using example, let's say I'm going from here to Iiit Bhubaneswar, right? Triple IT to Iiit Bhubaneswar. This is my source and that is my destination. And I have different modes of transport, of course. One is through the car, triple IT car, which can take 4 people plus driver at a given point of time. And it will probably take 40 minutes to reach. The second is to take the institute bus, which will take probably 40 people instead of 4 people, but it will take 1 hour for the to commute because we have to stop for synchronization. People will get off and get in and so on. So these are the two modes of transportation. One is the bus carrying 40 passengers, 1 hour duration. And second example is the car taking 4 passengers, 40 minutes duration. So which choice should I go for? Car. So it depends on what is my use case. If my use case is, after reaching IIT, I have to give a talk to this audience. Then it does not make sense for me to reach there earlier and then wait for the rest to come using the car where 4 people are traveling at given point of time, right? So if the goal is to reach IIT at the shortest amount of time, then of course I'll go with the car, which is the basically latency, the duration from source to destination. That's the latency. But if my goal is that because I'm anyway going to talk to all of you people, so it makes sense for us, it's okay, we can sacrifice or wait for 20 minutes extra, where like 40 minutes versus 1 hour. But like all of us can all like go in a single mode of transportation. So rather than taking the car and trying to transfer 40 people, which where it takes 10 trips, it's cheaper to wait for a bus, even though the initial latency from triple IT to IIT will be 1 hour, but still because our goal is to carry all the 40 people and I'm going to process all the 40 people together. So I'll go with a bus. So in this example, the 40 passengers at a given point of time stands for throughput versus 4 people in car traveling at a given point of time is the throughput of the car. And in this example, car is the CPU and the bus is any accelerators or any GPUs. So the reason why we are using accelerators more and more when we are talking about AI applications, large language models, and so on, is because like we are talking about terabytes of data, which means like how much amount of data and processing at a given point of time matters, right? Like of course, like how fast I'm processing matters too. That is, my latency also matters, but more than latency, my throughput is something that I need to care for. So that is one of the main reasons why many of the AI, we are switching our attention to the AI accelerators for the faster data processing because for better throughput, right? So yeah, we understood why throughput is important and why we should care for the throughput. So to summarize, the problem that we have or we are dealing with is data and compute requirement of the large language and AI models. And the solutions that we can offer is advancements in the hardware, having better algorithms, and having better data sets. Okay, so this slide. Okay. So this slide is taken from the Turing Award lecture by Hennessy and Patterson. So all through the world, anyone studying computer architecture, both at the PG level as well as the undergrad level, all of us have studied Hennessy and Patterson book. And those were the two people, like one was a professor in Stanford, another was a professor in UC Berkeley. And they won the Turing Award because of their contribution to risk-reduced instruction set computers, RISC architecture in the computer architecture domain, due to which AI is possible. So today we are able to have a hardware that can support the AI applications. That is because of the contribution of these two scientists. Like all the advancement in hardware, or computer architecture happened because of the contributions of these two scientists. And I was privileged to witness their turing award lecture, which they delivered in one of the conferences that I was attending. The name of the conference is ISCA, and it's a 4 A-star ranking conference. And they were the chief guests there, and they were giving this turing award lecture. And the slide is from their specific lecture. So now let's see what does the slide say. On the x-axis, we have the years, and on the primary y-axis, there is a typo. I didn't correct it because it's a screenshot. Nanometers, and on the secondary y-axis, I have relative power per nanometer square, right? So what does it, the orange line say? Technology nanometer, we see that it started from 180 nanometer in 2000, and like in 2024, we are inching somewhere near like 4-5 nanometer technology. And the blue line basically says that our power per nanometer square was less earlier, and it has proportionally risen to like somewhere around 4 watt per nanometer square. So what does this picture like convey? Why is this important for us to study? So before we get there, so because we have different like packages from diverse backgrounds, like semiconductor technology is one of the important focus areas of our government, as well as many of us are doing research in that. So what is exactly technology scaling? What are, like when we are saying we reduce the nanometer technology, what exactly are we talking about, and why is it needed? Why do we have to reduce the nanometer technology from 180 to 4 nanometer? Why is that important? Yes. Yeah. So this nanometer basically talks about the W by L ratio of the transistor. So if we are reducing the size of the transistor, then we can fit in more transistor in the exact same chip area. So more number of transistors means more computational capacity that we are getting in that exact same area. So we fitted in more number of transistors, which was Moore's law, which said that, okay, after in every 1.8 years or 18 months, we are actually going to double the number of transistors in the chip area. And that was backed up by something called as Dennard scaling, which was the power. So what Dennard scaling or power law basically talked about is if we are fitting in more number of transistors in the same chip area, then the power that is going to be consumed will be proportional to that. Right? So this is what was the Dennard scaling talking about. And this figure is taken from the power consumption models by like Professor Hadi Ismail Zadeh from his ISCA 2011 paper. Now, what the problem happened was, as we tried fitting in more and more transistors in the same chip area, there was a limit to it. It reached a saturation point. Why? Because when you're fitting in more transistors, the transistors consume energy and they dissipate energy. When they dissipate energy in form of the heat. So if I am placing two components very close to each other, the heat of this component is going to have an inductive effect on the second component too, which means that the whole chip is going to get heated up. And if it gets heated up, then it's going to have serious reliability issues. So when I try to give my processor chip what is 2 plus 2, it's going to give me 5 instead of 4. I'm going to have inaccurate, incorrect results. Nobody wants that. So that's why the next dip in the computer architecture was, or in the any processor technologies was to make sure that we are having less energy consumption. So before we get into this slide, if I draw your attention back to 2017, 2018 time frame when I was a PhD student and I used to work on graphic processor units, energy efficiency. I was not able to find any GPUs in the market to buy and do my experiments on. Why? Because Bitcoin mining was at surge. People all wanted to get rich by doing this by Bitcoin mining, and all the GPUs from the markets were gone, taken by the Bitcoin miners. So Bitcoin mining, yeah, some people got rich, and there was a lot of research in that. But one of the major backlash that the Bitcoin miners had to face was climate change. Why the climate change was a concern? Because they were using a series of GPUs for computing all those values. More GPUs, which means that the power or the energy that it was dissipating or the heat was too high. that it started affecting the climate change. So this was the correlation between having aggressively using computation resources without any optimization, how it actually affects the whole ecosystem or the whole climate as well. So that's the reason we have to make sure that whatever systems we are designing, yes, LLMs, AI systems are great, but we have to also make sure that 10 years down the line, we are still able to meet the computation requirements of the data that has been generated by sensor by different modes of data collection and still able to scale up our requirements. That is not possible without seriously looking at the power consumed by the like hardware resources that we're taking into account. So this slide basically shows the transition from 1980 to 2015. And on the y-axis, we have performance. So 1980 to 1985, we had CISC, complex instruction set computers, where like, let's say one instruction was capable of doing addition, multiplication, everything in one specific instruction. And the way the processor performance is calculated is how many instructions I'm able to process per cycle IPC. So then, so this is the main era which gave actually a massive jump in the performance, that is 52% per year. And this was the main contribution of David of Hennessy and Patterson, which got them Turing Award. How much time do I have? 30 minutes? Okay. Okay, thank you. So yeah, this was the main contribution of David. So basically Hennessy and Patterson, and they basically met in a workshop the way we are meeting, like different academicians were meeting in a conference or some networking platform, and they started scratching their heads over like whether CISC is the future or they should go with a risk reduced instruction set computer. So those who are not aware, so CISC to this, the only difference is, let's say in a CISC computer, I'm doing the computation, the addition and multiplication all in a single instruction. But here I'm breaking down into multiple instructions. So one is I'll take, when I'm doing any addition or multiplication, I need two data, right? A and B. So I will be having one instruction to load the data A from the memory to my computation, load another data B from memory to my computation course. I'll do the computation, that is my third instruction. And then the fourth instruction will be to multiply those data. So here we can see one instruction in CISC is broken down into 5.6 instructions in the RISC. Whole community laughed at them when they proposed this idea. Why? Because you are unnecessarily increasing the number of instructions, which means your IPC will go down. So this is not something that you're going to benefit. But many of our low-scale processors, ARL processors, and so on, they're based off of this. So all the like little cores that have mobile cores and so on, we saw a lot of performance benefit because of the RISC processing. And then came the better scaling. So what happened during 2005 time frame is, let's say you have invited some guests to your home and you are going to make some biryani for them. 50 guests are coming to your home. But the stove that you have has just one burner. That also is not helping. It's like has reached its maximum capacity and it's not going, the flame is not going up. This is kind of a crisis situation. What do you do now? Like I'm giving this example because all of us know what biryani is and like what processing time it needs, and everyone loves biryani. At least I do. So what do we do now? So I have invited 50 guests, right? And this one burner stove in my home is not helping, and there is no way I can use that to cook food for 50 guests who are going to come to my house in 3 hours time duration. That's my time limit. So what do I do in this case? Please don't tell Swiggy and Zomato. I don't have that much money to order biryani for 50 people. It's expensive. So what do I do now? Sorry? Pressure cooker. Okay. So I'll do some kind of fast processing with the same data. Any other solutions? Batches. I'll divide the data in batches. Yes. So that is exactly what pipelining is. So computer architecture uses all the concepts that we use in the Indian kitchen. So what else? I'll knock every neighbor's door. Do you have a spare stove too? I can borrow for a couple of hours, right? So I'll put some 10 stoves and I'll also get all the kadais and I'll divide my data, like my rice in different batches, and I'll try to soak the rice so that I can do some kind of pre-processing so that I can reduce my overall biryani cooking time, right? So this is exactly what multi-core processors do. So instead of having a very high quality single processor, I'll have video quality multiple processors. I'll process all the data at once. And this is exactly what multiprocessors are about. So even computer architects also got that idea, and they went to with the multi-core processing. Then came the Amdahl's law. So what Amdahl's law says, let's say I have a processor and I have an application. If I run that application on a like let's say on 100 cores, will I get 100x performance? Is that a possibility or not? So apparently, if I run my application on 100 cores, 100 parallel processors, I do not get 100% 100x performance improvement. That's not possible. There has to be a theoretical maximum which I can expect, and based on that, I will decide whether it's worth to invest time and effort on redesigning this algorithm or not. Same thing. Let's say I'm designing a new house. I bring my architect in, and then I say, okay, can you design my storeroom? The first question the architect is going to ask me is how much time do you spend exactly in the storeroom, how much budget you have in the storeroom. If I don't spend more than 10 minutes per day in my storeroom, it does not make sense for me to dedicate too much time and energy to redesign this storeroom. Rather, I should design my living room where which is basically the showpiece of my house, right? So exactly same. So how much time and energy should I dedicate for optimizing an algorithm if it does not theoretically give me a very high gain in terms of performance or speed up and so on. So that is what was Amdahl's law. Amdahl's law focused on making the common case faster. If an application, let's say my application has two functions, function A, function B. Function A runs for 80% time, function B runs for 20% time. It does not make sense for me to spend time on function B, which runs for 20% time. Rather, focus your energy, do compiler optimization, algorithm optimization, whatever optimization you can think of on function A, which runs for 80% time. That's what is Amdahl's law. And then now, what is next? So, Hennessy and Patterson actually answered this question by saying domain-specific architectures or accelerators. Switch your focus or attention to designing like CPUs or GPUs. Maybe go for when I say domain specific, I'm not looking at one specific application. I'm not talking about application specific integrated circuit. Rather, take whatever features or application that specific domain requires and try to put it in a chip. So some examples of domain-specific accelerators or architectures are neural network processors used for machine learning, GPUs used for graphics and virtual reality applications, programmable network switches and interfaces, and so on. So these are different examples that we should think of at this point of time. Why? Because they give us better performance. They might not have every functionality. That's not because we are not looking at generic. We are looking at specific things. So if this so one of the examples we can think of is autonomous cars, let's say. Autonomous car, what are the features that it needs? It needs image detection, object detection, transmission, receiving, and all those things. It does not probably need square root, trigonometric function support, and so on. So we can remove all those cores which do trigonometric and those special function things, and we can have those dedicated cores which do all this transmission, receiving. So object detection is just mathematical addition, addition and multiplication and so on. We can have more adder and multiply unit, and we can remove the units that do square root and trigonometric operations and so on. So that is exactly what is special purpose or domain specific architecture design. And by this, we are making sure that we are having some dedicated cores which are good at doing the functionalities that we need, and it also consumes less power comparatively. So, okay, so we know that how has the hardware actually evolved over the years. Now, let's spend some time and try to understand how has the deep learning hardware evolved over the years. So why is that the AI did not happen 20 years back in the line? So what was the limiting criteria? Why we did not see it, we could not realize it back then? So if we analyze the scaling of the deep learning workloads, we can see that it depends on the underlying hardware performance. On the x-axis, we have again the years, and the y-axis, we have peta. Flops is basically floating point operations per second. It's one of the measure of throughput, how much throughput we have, multiplied by days in training. So AlexNet, which came in 2012, it had the training requirement it had was like less than 0.1. And now we are talking about GPT-3, which is we are talking about several orders of magnitude higher, something in like 10,000 range. So as we can see, like the power or the throughput that we need has increased by several orders of magnitude, and that is because our hardware is able to support it. So before I go to this slide, so I would like to quote one of the examples. So okay, so many of us have actually learned about deep learning or machine learning from the lectures by Andrew Ng. So Andrew Ng is a professor at Stanford University who also works in Google Brain, and many of the LLM works and like maybe like all the AI works were one of his main contributions. He was in the team back then. So he did an experiment in 2010. So the experiment was to basically capture all the cat images from internet. So internet can be all the YouTube videos, like all the browsers and data and so on. So they needed about 48,000 CPUs to capture all the millions of cat images from the internet in 2010. And after the emergence of the GPUs in 2012, he repeated the same experiment. So, of again, identify the cat images available on the YouTube and the internet. So, the number of GPUs, can anyone know, like, guess how many GPUs that it needed to complete the task, which needed like over thousands of CPUs to do? Any like random thoughts is okay. No, not that great. So not two, but yeah, two-digit GPU. So like I think about some 16, 20 GPUs they needed to complete the same task. So that is the comparison because we have high throughput. So the data that was supposed to be processed by thousands of CPUs, we are able to do that using less number of GPUs. So yeah, basically the GPU inference performance have also increased by over 2x every year. So if here again, what I have put in the slides, this is a slide by NVIDIA. So the names Kepler, Maxwell, Pascal, Volta, Turing, Ampere are the different generations of the GPUs and the years in which they have been marked and the years in which they were released. And the K20X, M40, P100 are the specific GPU model names. And on the y-axis, I have int 8 tera operations per second. Again, it's measure of throughput, how much throughput they have. So as we can see, from the Kepler in 2012, we had 4 throughput, which scales up to 1248 throughput in Ampere, which was released sometime around 2020 time range. So what magic did it happen, or how it became a possibility? So the answer lies in, as we can see, in the Maxwell, the throughput was 7, and in Pascal, it became 21, almost 3x improvement. That happened because of NVLink, which supported GPU to GPU communication. Okay, so as we know, like all the biggest data center, I think a fifth biggest data center in the world, has some like 100 DGX systems. And each DGX system has about 8 A100 GPUs. So if I have let's say 100 DGX systems, each having 8 A100 GPUs, how am I going to connect like 800 A100 GPUs and how are they going to communicate with each other? So they are going to communicate with each other using some interconnection. So that's the reason they came up with something called as NVLink. So, okay, another thing that we need to keep in mind, GPUs or these accelerators do not have an operating system. They cannot run on their own. They are slave devices that needed to be connected to a CPU. So CPU is going to tell the GPU, you need to do this data, and this is the computation that you're going to do with this specific data set. So all the GPUs need to be connected to some CPU. So that's earlier what was happening. Let's say I have one GPU like say two GPUs, they have to be connected through the PCI bus to the CPU. And all the communication, let's say I'm going to copy some data from this GPU, it has to go all the way to the CPU, and then again like it will go to another PCI bus. So this was unnecessarily delay in the interconnection network latency, and that was cut down by using the GPU to GPU communication. So we had some high-speed interconnection network called as NVLink, which I'm directly connecting GPU 1 to GPU. So one-to-one communication. We don't have to go all the way to the CPU. Okay. So next, from Pascal to Volta, we saw about again 5x throughput improvement. That was because of the NV switch, high performance networks, InfiniBand connected GPUs. This was again like how we are connecting two different ports, having multiple GPUs for the faster communication. And again, they also had tensor core architecture, which had the flexibility of programming even smaller data sets. Like instead of FP32, we are able to now compute floating point 16 as well. Next came from 125 to 261 in Turing. That was because of we were able to represent better data types, that is int 8 tensor cores. And then the last, the Ampere, we were able to see we had tensor core support for sparse data computation and so on. So this is the different hardware and basically hardware improvements which help to get us or attain a hardware that was able to give us a throughput of 128, 1248 integer 8 data operation. Yeah. So what happens is that like typically the the machine learning workloads, there are a bunch of matrix multiplications. We have different layers. Different layers have different weights, and when the data passes from one layer to another layer, underneath it involves a lot of matrix multiplications. And some data are sparse data. So sparse data means it has a lot of zeros. So yeah, for dense data we can store, but in the sparse data, if there is some way that we can compress the data and store in less amount of and can do like this equally like fast communication or computation, that would be even better. Yeah, deleting the zero values. For example, I'll give you one example. So let's say I have a sparse data. There are two ways of storing a graph, right? So one is using a adjacency list, another is a adjacency matrix. In adjacency matrix, what will happen? We will have a lot of zeros. In the adjacency list, we will have lesser number of nodes that are connected. So this is adjacency list. When you have a sparse data, its adjacency list is a better way of storing the data compared to the adjacency matrix. So there has to be some way so that we can take advantage of the sparsity. So to summarize, the key components in the accelerating deep learning on the GPUs include different hardware advancements, which we talked about, that is NVLink, switch, tensor cores, and so on. There are also a lot of software advancements, like so you know that anybody who is working on ML extensively uses those libraries. Without libraries, would be not very like great idea to like write the training function on your own from the scratch. So this advancement was also fueled by a lot of software advancements like CUDA DNN, the tensor RT, TRTs, models, the different libraries like TensorFlow, PyTorch, Cafe2, DALI-10 pipeline, and so on. So now comes the analysis where typically my PhD work focused on. So my PhD work was on how do I make sure that my GPUs are doing the same performance. I'm not having a performance setback, but I can definitely reduce the power several orders of magnitude. How is that a possibility? How can I make sure that my GPUs are energy efficient? That was what my PhD is about. And I think today's world, every company is looking at the sustainability aspect. There are a lot of research on green AI, sustainable AI. So what they want to do is they want to do the same computation. Rather, the computation should scale up, but the power that it is consuming should go. That is what the focus of x-axis again I have the years, and these are the different generations of the GPUs that came different years. And these are again the model names of that specific GPUs, because the data that I have taken are from the white paper of those specific GPUs. And in the bracket, I have what technology node. So in 2010, Fermi was built on 40 nanometer node, and 2024, Blackwell is built on 4 nanometer. The blue bars are basically representative of the performance in Tera floating point operations per second, which is good. Like the higher the blue bar is good, because I'm able to support the higher performance. But the concerning part is the orange line. So the orange line, it represents power in watts. So as we can see that from the Fermi to Blackwell, that is from 2010 to 2024, my power in watt has started like increased from somewhere around 5 to like 35. 7 times higher in magnitude. So why is that so? Why is that this pattern that I'm observing? Any thoughts? Why is my power? Why has my power increased? Yes, of course. Like one straightforward solution is I have reduced from 40 nanometer. That is true. And also I'm trying to have different architectural improvements, like I have put in more interconnection bus, I have put in more memory. So these are all the architectural changes that we have made is responsible for this high power. And another important problem that we are also facing is the static power. So earlier, like back 20 years down the line during this time, so earlier we were only concerned about the dynamic power. So dynamic power means like I'm using that component, like how many times I'm accessing that component, dynamic power is proportional to that. But static power, what it does is, as long as the system or my system is plugged into the power supply, even though it's not used, but still there is a leakage current flowing all around, and it's actually consuming the leakage power or the static power. And the concerning part now is the static power has increased compared to the dynamic power because of the smaller chip size. So this leakage current is basically the reason for the leakage current is the less W by L ratio of the transistor. So yeah, here like the takeaway from this slide is my GPU performance demand has increased, but at the same rate, my power consumed has also increased. So I want the same trend in the performance, but I want to reduce the power. That is my goal. So now, okay, I'll spend about like 5 minutes to summarize what is my LLM computation, how we can take a quick peek at the LLM computation that is going on. So the transformers are the backbone of the large language models, and the transformers were introduced in a paper called as in 2017. It was published in a top-tier conference in the computer vision machine learning area called as MIPS. So it was published by Google Brain, and the name of the paper is "Attention is All You Need." So that is the name of the paper that introduced the transformer networks. So in this example, the transformer, let's take it as a black box for the time being. Here we are taking the sentence in one language and we are going to convert it into English language, right? Machine translation or language translation is what is the crux of this slide. Next, what goes inside the transformer network is encoders and decoders. The encoder accepts the input, decoders are going to give us the output. We don't have one encoder, it's a series or a stack of encoders. Similarly, we have a stack of decoders. I'm quickly browsing through the slides just in the interest of time, and I'll zoom on only one component, which actually makes them special. That is the attention. What is the self-attention layer? That's what I'm going to zoom on. And in the encoder part, we have two blocks. One is the self-attention, and then second is the feed-forward network. And typically, what happens is that it focuses on the self-attention. What it does, it focuses on different words in my sequence or my sentence. And it's going to calculate the correlation of a specific word to the other words in the sentence. That is what the weight calculation is in this example. And like decoder is also similar. It also has a encoder, decoder, attention layer in the middle. Okay. So here what happens is that we have the like input and then we have the output. Within the encoder and decoder, there is something that is like one of the vector that passes on from encoder to decoder is basically called as context vector. It stores the context of what does context especially mean. We'll see that in the next slide. It's a vector which has different weights. These weights are basically representative of the how relevant is my first word in the sentence to my current word in the sentence. How relevant is with the second word in the sentence to my current word and so on. It's going to calculate the relevance or the context of all the other words in the sentence to this specific word. I'll skip this. And they are converting or getting these values from an algorithm called as word embedding algorithm. Stuck. Okay. Yeah. So what I wanted to get at is this point. Let's say, what is self-attention? Let's say I have a sentence which says the animal did not cross the street because it was too tired, right? Now my question is, what does it refer to? The it, is it referring to the animal or is it referring to the street? What is the answer? It's referring to the animal, right? So what it does, this encoder and decoder layer, so the layer number 5, it calculates the basically context or the relevance of these words to the word it, and the intensity or the weight of this line is proportional to how important or how closely associated these two words are. So from here, we know that the it is referring to the animal and it's not referring to the. So this is what a self-attention mechanism is about. And what goes inside the self-attention mechanism? It calculates three vectors. One is called query, second is key, third is value. So these three vectors are calculated by X is the embeddings, which we are converting the each word in my sentence to a vector using the embedding algorithm, word embedding algorithm, and then I'm multiplying the each weight vector to get this vector. So at the end of the day, it's all about matrix multiplication inside the transformer layer. And the important function, which is self-attention, uses a series of matrix multiplication to find the values of these three vectors, which are going to be my input to my next layer. So applying Amdahl's law, that is making the common case faster. Matrix multiplication is one of the most commonly occurring operations in the transformers. That is the reason many of the research in the HPC, high performance computing or computer architecture domain focuses on optimizing the matrix multiplication application on any specific hardware, also looking at the how it can have a better matrix multiplication algorithm that can be optimized. So I think I'll end the session now. And at this point, like the rest is basically some of the interesting works that I did in optimizing the matrix multiplication on the GPUs. I'll skip that for now. You can read my paper and we can discuss offline whenever you want. Any questions from the audience? Sure.
Rates are decided by us or it is the computer which is deciding the rates?
So it's decided based on the model architecture. That's what I have studied so far. Again, I'm also new to the LLM domain. I'm trying to understand. So that is my understanding so far. So it depends on the which model we are going for. Yes.
Other deep learning models like CNN or SNet, we apply transfer learning technique. So this is LLM is also a deep learning architecture. We apply the transfer learning technique.
I believe so. Yes.
In what context?
So, for example, so this is an encoder decoder network. So there are a lot of other LLMs which are decoder only or encoder only. So we can learn from this like on a different data set, and we can use the same transfer learning to predict or do some classification on another data set.
On the side, provide content that
So using this word embedding algorithm, so how do we generate those words and what is the length of my context vector? It's all dependent on that specific.
first word is second word
Oh, so you are asking about how do I calculate the self-attention? Okay, so the self-attention we are calculating by calculating the query key and value vector values, and then we are feeding it into like there are also subsequent layers which are skipped in the transformer. So based on that, the weights are updated. We don't have just one weight. So after each layer of encoder, we actually are updating the weights.
That's like some of the bits I have seen are bits and words equal to one. Like this is not something that you have followed the words.
I am not very sure about that. Maybe I'm not the right person to answer. So I'm trying to learn. And this is and there are if there are any other characteristics, I'm yet to find out.
Thank you, Devasri ma'am, for enlightening us on this technology. So one of us working on machine learning, AI, and soft computing, but the actual code that runs on the hardware. So that needs to support the operations that we are proposing to do. So this actually opens our eye how we can just not think about processing the data, but how the data will run in the hardware, and also it should consume less power. So that is the eye-opening in this lecture. So I hope everybody learned a lot from this. And any query, any doubt ma'am is there at IIT Bhubaneswar. So you can reach out to her. And she is also open to PhD scholars. So any students they want to do heavy research in this area, they can contact ma'am. And so I am delighted to call upon Dr. Chinmay Panikrai sir to felicitate ma'am on this event.